Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Rafael Knuth, your host. I'm a contributing editor at Data Science Central. I'd like to start our event of today by thanking TIBCO for sponsoring today's event. TIBCO is a longtime supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. Today's webinar is entitled AI on Demand, Data Science and Operations, to be presented by TIBCO. Before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have 2 presenters who I'll introduce in just a minute. There will be a 10 to 15-minute Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speakers, Stephen Hillion and Nico Roth, both with TIBCO. Stephen Hillion has been leading large engineering and analytics projects for 20 years. He founded Alpine Data, acquired by TIBCO, to build a collaborative platform for data science. Before that, he led the global team of data scientists at Pivotal and developed a suite of open source and enterprise analytics software. Earlier, he led engineering at a series of startups. He received his PhD in mathematics from the University of California, Berkeley, and before that, read mathematics at Oxford University. Nico Roth is a data scientist at TIBCO Software, where he has spent the last year building out machine learning pipelines, consulting with customers, and extending the capabilities of TIBCO's data science platform. He graduated from Whitworth University in Washington with a degree in computer science. Thanks for being with us today, Stephen and Nico. We are looking forward to your presentation. AI is right here, right now, and changing our lives. The ever-present need for business optimization, combined with a long history of applied statistics, explosive growth in data, and recent advances in cloud computing, has created a perfect storm of innovation. In today's Data Science Central webinar, you will learn applying AI insights in real time to enable optimal business decisions, real-world examples of AI-powered recommender systems, continuous closed-loop learning, and techniques for analysis of very wide time series data, and how to take advantage of TIBCO. Stephen and Nico, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thanks very much, Rafael. This is Stephen Hillion, and it's a pleasure to be here. Had some connection with Data Science Central for several years now, and it's a great platform, great community, and so we're delighted to be here. We're going to be talking, you can quickly read through the disclaimer there in a couple of seconds. Okay. We're going to be talking about, our perspective on artificial intelligence and machine learning, how after really several decades of development of powerful algorithms and high-performance computing platforms, there's nevertheless an array of technologies these days that actually makes it, dare I say, fairly easy to apply machine learning to real-world problems. And we're going to show you 2 examples drawn from projects that TIBCO's data science team has led that show how you can deploy AI on demand without a great deal of coding and ab initio development. So I'll start by spending just a few minutes giving you sort of my view of how AI and machine learning has come full circle, really, since its inception in the 50s. And that's really when AI and machine learning got started. It's actually when neural networks, for example, were invented and applied in lab settings. For example, the SNARC SNARC project at Harvard, I think it was, where neural networks were used to power a robotic mouse that found its way around a maze. Of course, Alan Turing, known as the father of computer science, was also, in some senses, the father of machine learning, sort of coming up with early ideas around genetic algorithms and how machines could learn from their environment, store that data, and use it to essentially reprogram themselves as time went on, which is a pretty good definition of machine learning, as far as I'm concerned. But anyway, doubts and sort of doubts about the sort of the academic nature of these methods, about the practicality of them, and also limitations in computing power at the time really led to what was termed the AI winter in the 1970s, where there was comparatively little development in the world of artificial intelligence. Nevertheless, the methods of statistics and machine learning started to exit the academy and come into the world of software. And so you had the rise of companies like SAS that started off with applications in agricultural sciences of machine learning methods and regressions and so on, made easy to use through a software package. And also you had SPSS coming from the social sciences. R came along a little bit later, but the forerunner of R, the S language, which actually has a pretty significant connection with TIBCO, was invented in the 70s. So you started to have these methods being available to everyday business users. And then in the 1980s, what for me is sort of the big significant development around analytics was the rise of databases. So now new storage mechanisms that allow people to store and query their data, which they could then use in these new applications. So you had the beginnings really of the classic sort of analytics stack of back-end computational power in the databases and then front-end algorithms to be used by data scientists. In the 90s, you had this explosion, really, of AI. First of all, sort of back in academia with the rise of new methods, ensemble methods, random forests, new support vector machines, but also in the public eye, especially with the defeat of Garry Kasparov by Deep Blue at a game of chess, and a chess tournament in the 90s, really brought AI into the foreground. And then, of course, most of us are going to be familiar with how things really got going very rapidly in the 2000s with the onset of much larger and more diverse data sets being championed and used by the big Silicon Valley companies with the development of new computational platforms, the successors to those databases, the MPP databases and parallel computing platforms like Hadoop, that were then used by companies like Google and Yahoo and, of course, Netflix with their Netflix challenge to do really innovative things. So you had this convergence of big data computational platforms and accessibility to these various and diverse data sources and all the algorithms that had been sort of developed over the previous decades. And I think what's happening now in this decade is things have, in a sense, come full circle. Now that you've got convergence of all these technologies, we can go back and rediscover a lot of those algorithms and empower them with this new technology. The perfect example of that, of course, is bringing back deep learning bringing back neural networks in the form of deep learning, which is, of course, used throughout industry these days to do all sorts of clever things, including recognize pictures of cats. There's a little cat there that's been sent through a neural network looking a little sorry for itself. We've actually, maybe a little bit more practically, use some of these methods ourselves in our software. What we're going to dwell on today is really how we've used the TIBCO data science platform and open source technologies for practical use cases. And Nico is going to give us a demo of a couple of those from two different areas of the world. But I actually want to start off with just a quick review of how we've actually used AI in our own applications themselves, using artificial intelligence and machine learning to deliver recommendations to users. So again, we're going to focus on applications of our technology, but within our technology, we've used AI, for example, in Spotfire, our well-known data exploration and visualization suite, in its latest version, Spotfire 10, uses AI to auto-suggest what you should be looking at when you're exploring a data set. So when you attach yourself to a data set in Spotfire and maybe select a field, will automatically suggest other fields you might want to look at that seem to be important in terms of its predictive power in relationship to the field that you've selected. We'll also use natural language querying so that rather than have to construct dashboards yourself, you can just ask questions of your data and we'll automatically suggest which charts or which fields you should be looking at. Here's an example from the world of churn in telecommunications, where you pick a field like customer status and ask, well, what's related to customer status, which is in a sense saying, how can I predict churn? And we'll actually recommend fields that seem to be related to that and recommend visualizations that will actually give you insights into what is causing a change in customer status. Anyway, let's get into a real-world demonstration of this power now. So again, we're going to be using a lot of the techniques here that have been built up over those decades, and a lot of the technology to illustrate two fairly sophisticated examples. The first one is in the area of risk management. Now, if you go into the TIBCO cloud, you can actually find an application that we've built that's actually fairly general in its application to risk management, risk investigation. We're going to apply it here to a specific case around fraud detection in financial services, specifically credit card fraud. What Nico is going to show you, and this is all available in the cloud, it's all web-based, and it uses the entire TIBCO analytics stack, including, as I say, some open source technologies. We're going to show you, first of all, how we visualize the application. So what does the end user see? And in this case, we're seeing incidences of fraud around the country which have been classified with supervised and unsupervised methods. So supervised stuff telling us, you know, this looks like something that happened in the past that turned out to be bad, and also unsupervised in the sense of this just looks kind of weird. And then using our live apps capability, where you can actually build applications in the cloud without writing a lick of code, we can actually drill down into those cases and actually submit them through a sort of CRM process. And then we'll show you how we actually built that. So how do we actually predict those fraudulent cases? How do we do the analytics in the back end and chomp through all of that credit card transactional data? Okay, so Nico, I'm going to hand over to you now so you can actually show us this in action.
Perfect. Thanks, Stephen. I'll go ahead and share my screen. I just want to confirm that you can see it.
Yep, there it is.
Perfect. All right. Yeah, so like Stephen said, this first example that we're going to go through today is really geared towards fraud and risk detection. So we're going to start out looking at a TIBCO cloud application. That's what you see on your screen right now. And it leverages a combination of different types of machine learning models. And its objective is to detect fraud and other types of anomalies. But it also allows you to score data, raise investigations into different cases where risk is flagged or identified. It allows you to track it afterwards, but also you're able to continuously take in new data, right? The results of these investigations into fraud and apply it to the models and let it continuously learn over time and improve over time. So we'll just jump in real quick. And the first thing you're going to see here when it loads is a Spotfire Geographic Map. And it's going to take up the bulk of the dashboard here. You can see a map of America and different spots kind of scattered around the map. Now these spots are colored by oddity or high risk of fraud. Basically what's going on here is it's just flagging transactions that are fishy. So a risk analyst can come into the dashboard and start an investigation into one of these single transactions, or you can filter down to a state level and start an investigation into a particular state or what be it. So my role as a data scientist dictates that I'm really in charge of the modeling portion of the application. So for that, we're going to head to TIBCO Team Studio. And Team Studio is a collaborative platform. It's really designed to support the entire analytics lifecycle. So it simplifies data prep, machine learning, deployment within big data systems. It's really an end-to-end solution. And here we find ourselves in the risk management project space. So in Team Studio, you have projects that are broken down into different pages like this. So we can see, recent activity here. I've been quite active in this workspace. We can also see the other project members here. If I want, I can add, subject matter experts, other data scientists, product manager, whoever's needed, I can add to the project, and they can sort of overview it or contribute to it. Another tab is the Data Sources tab. And this is where we see all the data sources that are available to this project. So Team Studio can connect to most relational databases, and it also supports all flavors of Hadoop and Hive and Spark. So it's pretty robust. But really the work file tab is the heart and soul of the system. Work files are where you create the visual workflows that dictate the entire machine learning pipeline. And we'll jump in to sort of give you a better picture of this. This first workflow is where we've trained the models. These models are what supply the dashboard with the end results or the fishy transactions. So the left panel here is a list of all the operations you can do, or operators. and you can just drag and drop them onto the canvas. So, let's say I want to use a column filter. I would drag and drop. I would connect to my data set here, just link it up, and from here I can choose which columns I want to keep or filter out. But I won't get too much into the mechanics of Team Studio. One thing to also note is you have this data tab up here, which allows you to see which connections are associated with this workspace. If I want to bring in another data set, again, it's as simple as just dragging and dropping. So this workflow, we managed to build the models, and we've done it with no movement of data. So every row filter you see, every null replacement, these algorithms here, everything is pushed down to Spark, and it's done in database. It's done on the data set sitting in Hadoop. And again, we're able to leverage the whole power of Spark with basically no code. So it's a pretty powerful platform. But the goal of this particular workflow is to generate an oddity score, which really provides us with a sense of how odd a particular transaction is. But it also provides us with a probability score that predicts how likely a transaction is to be fraudulent. So we'll start out with the oddity score. Actually, we'll start out with the data set. So we'll take a look at what it looks like. And you can see we have a number of different columns here. We have the age of the account, the value of a transaction, what sort of channel it went through, and various other columns here, metrics that we're collecting. But we also have a label here, a 0 or 1 to determine or to indicate whether or not this transaction was fraudulent. Now, it's always good to get some sense of what data you're working with. So we can get a quick 50,000-foot view of the data through the summary statistics. And this tells us things like, what are the contents of the data, right? How many empty values do we have? How many null values? What are some of the most common values for a given column? What are standard deviation? So this gives us some nice information here. And fraud is typically known as a rare event type problem, and we can confirm that by plotting the label. And we can see that, yes, fraud is definitely a rare event. So now we'll move down to the first part of the branch, this downward branch, which produces the oddity score. So the first step is to apply PCA, which is principal component analysis. And this basically just lets us know, which columns are the ones that we really care about, which are the columns that should be used to train a model. So we get those columns from the PCA, and then we cluster based off of those columns. And we use the clustering to determine the oddity score. So how far is a particular transaction from the centroid or the center of a cluster? And we use that as our oddity score. The second part of the modeling can be seen on the right branch here. We follow best practices and split into training and testing. And we trained 3 different classification models. You can see random forest, gradient boosting, and logistic regression. We also can evaluate those models here through the confusion matrix, ROC, and goodness of fit operators. So we'll look at the logistic regression. We can see the coefficients, p-values, standard error. But we really want to see how does it perform compared to the other models. Here we can take a look at the top. It lets us know that, yes, the logistic regression is actually the best performing with 0.986 accuracy compared to lower for the random forest and gradient boosting. So logistic regression is our champion model, and we'll go ahead and export that. Now, it's to be noted here that you can export a model within Team Studio as a PFA or PMML, and you can deploy it for real-time scoring. We're not going to use that for this use case, so I'll show you what we're going to do in a second. But after we've trained the models, the next step is to score new data. So we have that in another workflow. So we'll navigate there now. You can see we have some other files in this project space, but model scoring is the flow we're interested in right now. Now, what this workflow is doing is it's taking those 3 pre-trained models that we just saw, and it's using them to predict on new data that is coming in. So it, again, generates an oddity score from the clustering and a probability of fraud using the logistic regression. And you can see we load those data sets in, or those models in here, sorry. Here we load the PCA model, logistic regression, the k-means. And then after we replace the nulls, we have new transactional data here. So we'll combine those generated values, the oddity and the probability, into a single data set, and we're going to copy that data set to Redshift. So when we copy this to Redshift, what this is doing is it's supplying the geographic dashboard in the live app that we first saw when we first started out this demo. So we have the 2 main pipelines in place, right? We have the training, which was the first flow, and now we have the scoring, which is this flow. And we can move on to the next step, which is automation. And within Team Studio, you can create jobs to run flows on a hourly basis, minute basis, weekly basis, et cetera. So we want to score new transactions every day, and you can see we run this once a day. And you can change this or edit this, but it looks good to us now. And we also retrain the logistic regression model every week on the accumulated new data that we have. And constantly refreshing and retraining keeps the live apps dashboard up to date. So it's really important that we do this. And we can really see this come into play when we step into the role of a risk analyst who uses that dashboard every day. So we'll go ahead and do that. And we'll go back to the risk analyst dashboard. And again, just to reiterate, the spots are colored by fraud. So yellow means they're like past fraud, or they have high probability of being fraud. Green is that they are odd, they had a high oddity score, and red, as you can see, means that they have both of those. So what defines high? How do you define high probability or high oddity score? Well, the analyst can come in here and they can set a threshold. So right now, high to us means 50% chance of fraud and an oddity score of 15. So let's say we want to launch an investigation into fraudulent cases in Texas. So we can click on the state of Texas in the map, and we can go ahead and create cases. So this is a filtered list of fraudulent or potentially fraudulent transactions. We can go ahead and select one of them in Texas, and we can create a case for it. So we're going to type in a very informative comment here. And we're going to jump to the case details. And you can see at the top, these are a series of predefined steps that a risk analyst would follow to determine whether or not this case is fraudulent. So we're going to go ahead and do that. We're going to assign ownership to, we'll give it to Marion. She's not doing anything. I know she's slacking off. So we'll submit it. And Marion is pretty sure that this is fraudulent after looking at it long and hard, so she's going to resolve it. And the final step in this process is to label it. So we've completed an investigation, and what is our conclusion on that investigation? Well, we think that this particular transaction is fraudulent. So we'll label it as fraudulent, and we will submit this ticket. So now we've had an investigation that is started and completed, and we determined that it is fraudulent. And what is actually going on here is we're taking this transaction and the label and copying it to Redshift. So we're basically generating new data here. So we'll jump back to Team Studio, and we'll take a look at the process of retraining a model with new data. So we'll look at the third and final flow here. And at the top left corner, you'll see the new investigations. And these are directly from the risk analyst. So are they fraudulent or undetermined or no fraud? We'll filter out the undetermined because we're only interested in yes or no. We'll join it with the new score transactions as well as our overall corpus of other transactions. So we have the newest up-to-date set of transactions here. and we'll do data science best practices, replacing nulls, random sampling, resampling. And then we're going to load in the champion model, the model that is currently in production. And we're going to train a new logistic regression model. And we're going to compare the two. And if the new challenger model performs better, then we'll go ahead and replace the current model in production. So that's exactly what happens here. The new challenger model performs much better. So we're going, well, marginally better, but still better. So we're going to export that here. And this will be our newest up-to-date model in production. So throughout this whole process, we've seen how you can leverage a combination of different machine learning models, supervised and unsupervised, pitting different models against each other to determine the best one. And we do all this to predict fraudulent transactions. And once we have those predictions, we can expose the results to an analyst application like TIBCO Live Apps. And then within the Live Apps, we are able to generate new data and continuously learn and retrain the models based on that labeled data, courtesy of the data analyst. So I will hand it back to Stephen to talk about another interesting use case that we've been working on for the last few months.
Great. Thank you, Nico. I want to emphasize just a couple of things from the demo that Nico was just showing you. First of all, as I think both of us emphasized, to build that application, what we've tried to do is provide technologies in such a way that reinventing the wheel and building stuff from scratch is not required. So putting together a case management application is really sort of a process of assembling pre-constructed materials. Selecting algorithms to use is, of course, the artistry of the data science, but encoding those so that they run in platforms like Redshift or Spark or Hadoop or Hive isn't something, again, that the data scientists should have to worry about. So as much as possible, what we try to do is to make this sort of code-free, easy-to-use AI on demand by the data engineer, the application developer, the data scientist. And just to pick up on one specific case there, when you're looking at a workflow like this one that Nico built, those data sets, which in this particular case are sitting on a Hadoop cluster, which could be EMR in the cloud, HD Insight, or Cloudera, say, within your firewall, at every step of the way, whether that's as simple as a row filter or a frequency chart or as complicated as a random forest or gradient boosted trees, all of that is executed in the underlying platform. So if you've got a very large data set containing credit card transactions and you want to cleanse that, prepare it, build features, develop your models, and test them, at every step of the way, we're pushing those computations down. We're pushing those calculations down as a Spark job or a Hive job or SQL, so that we fully leverage the parallelism and the power of the underlying platform. So as easy as that looks in the sense of being able to just drag operators on, apply them in sequence and build your models, and as easy as it in fact is, it's actually doing some pretty sophisticated stuff on the back end in terms of turning every single one of those data science instructions into the language of the underlying platform. Okay, let's move on to our next demonstration now. The one that you just saw uses fairly standard, sort of tried and true techniques from data science in order to yield the models. Here we're doing something that actually involves the same sort of platform components, but some rather newer algorithms that were developed by TIBCO. So I'll set the stage a little bit, and then Nico will drill into this in more detail. This is coming from the world of manufacturing, in particular some collaboration that we've done with a manufacturer of integrated circuits in Asia. And in this case, the goal is to essentially create a digital twin of the manufacturing process, a digital twin of the fabrication plant. And what we mean by that is essentially constructing a predictive model that replicates what's going on the factory floor. So when a wafer of integrated circuits goes through the manufacturing process, there may be many of these processes. These days with these larger, more complex chips, you're really talking about dozens of layers and thousands of process steps. So as we go through the process step, we take measurements. Those measurements may be of pressure or etching thickness or temperature. And each sensor is constructing then a time series of these measurements at every second or minute taking measures of, say, temperature, so we know what's going on at every step of the way. So thousands of sensors, thousands of measurements. And you can think of each of those as a variable. Does this measurement at this point in time somehow have some predictive power in determining how the wafer performs at the end? Because at the end, we take the wafer, having gone through these process steps, and we perform a series of tests for computational accuracy, for speed, and we decide whether something is successful or failed, and we call that the yield, how much we actually get out of the process. And essentially what we want to do is build, as you see at the bottom here, a model of how yield relates to these individual process parameters, these input variables. So in that sense, it's sort of a classic machine learning problem. We've got a dependent variable we want to predict in terms of these input variables. What makes this really challenging in terms of building this digital twin model is that the data is both big and wide. So they're not just many rows. In other words, we have many lots and wafers going through this process. We also have many variables, many columns. There's, as I say, thousands of sensors with thousands of individual measurements. These time series are at each point creating a variable that might be of interest. So how do we essentially perform something like a regression of one variable against millions of variables, and do that very quickly, because we want to be monitoring this almost in real time so that we can send information back to the factory manager so they can go and investigate or maybe even pull the wafer off of the lot. So the way we've done this is to leverage an architecture that uses a variety of different techniques, in particular uses Spark for rapid processing of large quantities of data, and again uses that Spotfire dashboard to show those results to the end user. So starting on the right here, we have the Spotfire dashboard, and Nico is going to show you what we actually display, and it's remarkably intuitive and easy to navigate, so I can understand what's going on, what's causing what, and then drill into that. And then over on the left, we power these dashboards, these simple dashboards, through these sophisticated workflows built in the TIBCO data science platform that uses a variety of standard techniques, some of the random forests and the data prep type operations that we've already seen, but also novel methods, time series encoding methods, wide data variable selection techniques for trimming down that million variables into something more manageable. So Nico, why don't you show this again, how this works in practice?
Sure thing. Let me share my screen. Stephen, can you see my screen?
Yes, I can.
Perfect. All right. Yeah, so we're going to totally switch gears here, moving from finance to manufacturing. And like Stephen mentioned, this particular demo is actually very heavily influenced from a project we've been working on over the last few months. And it really revolves around analyzing large amounts of sensor data from a manufacturing process to determine the root cause of product yield. And once you're able to know that, then you can ultimately increase your outcome or your yield. So the example that we're looking at today focuses on yield for semiconductor wafers used to make chips or integrated circuits. But really, the methods that we've used for this problem can really be applied to a wide variety of different settings. Any application where you have an outcome that you're interested in, and that outcome is influenced by sort of a haystack of variables, and you want to find that needle in the haystack. So digital advertising, where you want to track many different URLs that customers visit to draw some conclusion about their profile, or genomics or gene sequencing, whatever it may be. There's a wide variety of different use cases. But in this case, we've created a digital twin for semiconductor wafers. And Stephen touched on it a little bit, but at a very basic level, digital twins are virtual representations of some physical system. But really, it's just a mathematical model, right? It simulates, in this case, the manufacturing process. And they've been around for a few years, but they've really shot up in relevance due to breakthroughs in machine learning, being able to actually predict, and IoT devices, of course, enabling the collection of massive amounts of data. But the backbone is really advancements in big data analytics, being able to actually chunk through that massive haystack of variables or of data, and which in a lot of cases, ours included, translates to literally millions of variables. So we'll get into it a little bit here. If you take a look here, sort of in the middle of the screen, the process flow, the first thing you should notice is that it's broken down into a series of steps, P1, PI, PI plus 1. And the number of process steps is pretty variable depending on the use case. But the latest processes for, I know for 3D flash memory, are upwards of 1,000 process steps. And at any given step, there's a collection of sensor trace data. So think of classic measurements here like temperature, pressure, diameter of ball bearings, whatever it is. Anything that can evolve over the duration of a process step. Those changes are captured and visualized in sensor traces. So thousands of sensors, each sensor with thousands of sensor traces, all of which have potentially relevant information that affects the yield or the outcome. What you're really looking for is which point of which sensor has the highest association with poor yield or good yield. So once all the processing and the measurements are done, then the product is tested. So a wafer goes through sort of a pass-fail scenario. And if you aggregate all the pass-fail data, then you're left with percentage yield, which is just simply the percentage of, or the ratio of products or parts that passed. And then, of course, the inverse of this is the percentage of failing parts or yield loss. So knowing the yield loss or the yield, it gives you a baseline level of value, but you really want more information as to where in the process did things go wrong. At which sensor, at which point should I be looking at to correct the increase in yield loss. So you can actually use the process parameters, right, the process steps and the sensor measurements. You can use those to build a model. So your yield right here is a function of all the process parameters. Think of it almost as like a standard regression. Your dependent model is the yield, and your predictor parameters are all of the process steps or all of the sensor readings from each sensor at each point in time. Very simply, that is the digital twin for yield model. But as Stephen brought up, a challenge that we very quickly run into is the sheer amount of data that you have to process. Again, if you have thousands of process steps, thousands of sensors, thousands of sensor traces, you're looking at millions of input parameters. So millions of variables that you have to regress on. So it's not trivial, and some sort of big data technology is going to be needed. But we're going to jump into the dashboard here, the analytics portion. So here, imagine we've already created the digital twin. We're at the end step. We're getting insights on individual sensors and time periods. This is what we would see then, the Spotfire dashboard. It contains the final output. This is what a factory manager would be looking at to digest the results of the digital twin. So here at the top, you can see we have yield loss by lot, and we have fairly low yield loss, low variance from yield to yield. Everything looks pretty hunky-dory here. There's low levels of yield loss. Now the heat map here, the rows are indicating a particular sensor, so sensor 4, 5, 6, so on and so forth. And then the columns represent the time periods. One full row would be, or time point are the columns, and one full row would be a full time series. And it's colored by variable importance. So at this point, at this time, this is how important it is to the yield outcome. And again, this is a particularly healthy time frame, so we don't really see anything interesting here. But if we go ahead and rerun it and grab the newest results, all of a sudden it's much more angry at us. And what happens when we rerun it, I'll dive into more detail in a second. But what happens is it runs a Team Studio workflow in the background that generates this list of variable importance, and it colors or populates the heat map. So at the top, you can see again that we have much higher yield loss. And we want to go ahead and dive into this look at these lots that are troublesome, and it looks like sensor 4 here is really what's given us the issue. So we'll drill down not only to the problematic lots, but also to the particular sensor and time points that are indicated to be of importance. And we can see that immediately there's something going on here, right? Green means it passed, it's a normal wafer. Red means it's abnormal. And we can see that the normal ones have an elevated sensor reading. So think of this as pressure or temperature. Whereas the ones that are failing have lower readings for time points, looks like 6 to 13. And if we go back and we look at the original data that we first saw, and we take a look at what that might look like, you can see that there are no normal or abnormal outcomes, and it's just one continuous line chart. So if we drill back down to the abnormal, we can see that, again, something at sensor 4 at these time periods has some effect on yield. And this is actually pretty important and pretty cool because we can directly link yield loss, right, sort of raw numbers, to a particular time period at a particular sensor at any point in the process flow. And we're able to do it very quickly in a nice and visual way. So how does this happen, right? How do we get to this point? How did we create the digital twin? How is this heat map getting populated with these nice colors? And that's a tough question. There's a lot going on here, so I'll do my best to try to distill it. But the core of it happens in TIBCO Team Studio, or TIBCO's data science platform. And this is what we saw in the previous demo, and it's also what we see right here, right now. So the workflow is comprised of 3 main steps. The first step is to reduce the size and the complexity of the time series data. We have large amounts of observations and large amounts of columns or time periods, so we need some sort of variable reduction method, and we chose to use SAX encoding. Basically, it just compresses the time series. So with the reduced size, you can then very easily compute correlations between the outcome of the manufacturing process, whether or not it passed or failed, and the thousands of input variables. Once you do that, then you can filter to those highly correlated variables, and now you have a vastly reduced data set, and you can feed it to a standard random forest regression. And the random forest regression supplies us ultimately with the outcome or the variable importance metrics. So we'll go into a little more detail. First, we'll take a look at the input data set. You see it's in tabular format, and this is representative of time series data. So for each wafer and sensor, you have a unique time series. And these are fairly long time series. I can keep on scrolling, but to save us time, it's just about 1,000 columns or 1,000 time points. So fairly wide. And if you have hundreds of sensors and thousands of time points, we're looking at potentially millions of variables that can influence the outcome. So those are millions of variables we have to compute the importance for or regress on. And as a lot of you probably know, it's not exactly easy to feed millions of variables into a standard regression. And that's where SAX encoding comes in. So very simply, SAX encoding reduces a wide time series to a smaller number of aggregated values. And I'll show you a visual example of that. If we isolate down to one time series, so one wafer, one sensor, one time series, we see this is what it looks like. It has about 1,000 time points. There's a slight trend upwards, and you have some landmarks scattered throughout the data. But if we isolate down to the same observation after the SAX encoding, we look at this. It's reduced it to about 50 time points, but it still maintains its informational integrity, right? You can see the same landmarks, the same upward trend throughout the line chart. So the SAX encoder compresses data, yes, but it also pivots it. you'll notice that this is not in a wide format anymore. It is tall and narrow. And this just allows us to work with the data a little easier. We still have some other variable reduction methods ahead of us. So working with it in this simpler tall and narrow format makes it a little bit easier. We can see that the output of the SAX encoder is about 30 million rows. And for each time series, we have, again, about 50 points. The next step is to take case failures, so whether or not our particular product failed, 0 or 1, and join it together with the output of the SAX encoder, which is what we see here. And then we have our next form of variable reduction. And for that, we chose to use a wide data variable selection operator. And really simply, this just computes correlations between the input variable, right, a particular sensor at a particular time, and the outcome. So in this case, failure. We can see here the dependent variable name is failed. We have some other parameters here that we can configure, all code-free. And we can visualize the outcome or the correlations in a histogram. We've got a nice little bell curve here. And really, all these values in the middle, we are not interested in. Right? We are interested in highly positive correlations and highly negative correlations. So if we take a look, we can see, we're really interested in observations from about 0.189 upwards and 0.175 downwards. So our next step is to filter to those observations or those time points which fit within those correlation range. And then we'll join it back to the original observation data set. So we'll get all the values that we're interested in. And then now we've actually reduced our variable space by quite a lot, right? We started out with millions of variables. And now if we unpivot it, or pivot it, excuse me, you can see that we're just dealing with about 30 variables, right? So particular sensors at a particular time point. So we've gone, again, down from millions just to 24, a little more, through the process of this flow. And with this reduced data set, it's very easy for us to feed this into a standard regression model, right? We have 30 variables. So in the alpine forest regression model, or random forest regression, you see we set the number of trees to 10. And we've taken these variables and trained on the ones that we just care about or the ones that are highly correlated. And the output of the random forest regression, you can see, is a variable importance metric. And we see that sensor 4 is really the most important variable at various time points here. And this is consistent with what we saw in the Spotfire dashboard. So at each stage of this workflow, right, the row filters, the visualizations, the three algorithms we talked about, SAX encoding, wide data, and the regression. Much like Stephen said, these are all pushed down to Spark. So these algorithms are running directly on the data set that's sitting in Hadoop. So no data is moved, and we have very, very high scalability. And even with millions of variables, this flow runs in just a few minutes. So that is the digital twin for yield. And I'll go ahead and give it back to Stephen to close this out.
Great. Thanks so much, Nico. That was nicely explained. So not too much to add to that in terms of that demo. I think we've got a good overview there, again, of using the sort of combination of technologies in order to yield something, if you'll excuse the pun, fairly simple to the end user, but which is backed by a lot of power in terms of those algorithms and that computational back end. And one thing I wanted to mention is that a lot of these techniques are actually available for people to try out on the TIBCO community. One thing we didn't talk about in that demo, of course, is how we sort of define what is anomalous in the world of manufacturing. We talked, of course, a little bit about looking at measures of yield. But in fact, there are lots of ways that we decide what is bad and what is good. And in many cases, it's not enough just to look at crude metrics of test passing. For example, suppose you want to determine if something's going wrong right in the middle of the process before you have any objective metrics. Well, that's where we have methods for anomaly detection, for example, which are available for people to try out on the community, the TIBCO community, where we actually use neural networks with hidden layers to, if you like, reconstruct the search space of process steps and wafers in lower dimensions, and then reconstruct them, and then look for anomalies, where the anomaly is essentially something that, kind of like my poor little cat at the beginning of the demo, doesn't seem to make it through the reconstruction process, doesn't seem to make it through the neural network very well. In other words, almost by definition, it's anomalous. It's outside of the norm of the data set as learned by the neural network. So some nice techniques there for how we actually define what's anomalous. And then we can actually use that as the dependent variable and then drill into the root causes. Other accelerators and templates that you can find up in the community that are available for Spotfire and for the TIBCO data science platform. So we encourage you to try those out. Okay, well, I think I'm going to hand back to Rafael and maybe open up for some questions.
Stephen and Nico, thank you for the excellent presentation. And we'll get started with today's Q&A session, and I want to thank the audience for their participation. We have a great many questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up the screen with contact information for Stephen and Nico if you'd like to contact them for a copy of the slide deck following today's webinar. So let's get started. What sort of performance can we expect from some of the algorithms you showed today?
Right, that's an interesting question. As I said at the outset, one of the reasons why we're using some of these techniques in terms of being able to reduce variables and some of the open source platforms like Spark and Hive and so on is so that we can chomp through the data pretty rapidly. In the particular case that we've been working on, this is a fairly major project that has yielded some of these innovations here. We have very powerful clusters that are running through these things in fairly short order. So to be more concrete about that, I know we've run internal tests where, say, on thousands of wafers, thousands of observations, if you like, and millions of variables corresponding to, thousands of sensors. So, sort of thousands of observations and millions of variables. We can run through a flow much like the one that Nico showed you in the order of a minute. In the real world, where we have many more observations that we need to process, we can typically get through, say, something like 100,000 observations, again with a million variables. So, about 100,000 times a million in about 10 to 15 minutes on a modest size cluster. And that corresponds to about 2 to 3 terabytes of data. So those are sort of some rough performance numbers for stuff that we've seen both in the lab and in the real world.
Thank you, Stephen. Next question, where is TIBCO Cloud hosted? AWS, Azure, do we have a choice? Right.
So TIBCO Cloud itself, so TIBCO's own hosted infrastructure is I believe, hosted on AWS. But the TIBCO data science platform can actually be deployed pretty agnostically. So you can run the data science platform that Nico was just showing you on Azure. You can run it on GCP, on Google. You can run it on AWS. So it's pretty agnostic. It's defined to run pretty much anywhere. But I want to emphasize that we actually try to take advantage of the platforms whenever we can. So a couple of examples of that. For example, say in the world of Azure, you have the Azure SQL Data Warehouse, which is very frequently used as a relational database in Azure. We support that as one of the platforms that we can connect to and cleanse the data, again, by pushing down instructions. Azure SQL Data Warehouse is really good at filtering and pivoting and transforming and cleansing data. So we take advantage of that through this sort of drag-drop interface. In the world of AWS, for example, we take advantage of EMR, their flavor of Hadoop, and Redshift as their particular database. So when we can, we'll take advantage of cloud-specific storage platforms and computational platforms so that you can use the data that's already resident in the cloud, and more importantly, use the sort of elastic nature of the computational platforms that are available in the cloud. So the simple answer to the question is we can kind of do it, not only can we deploy on the ones that you mentioned in your question, what was it, Azure and AWS and GCP as well, but we go further than that in that we actually leverage the underlying data platforms.
How can we analyze application logs with some machine learning model to determine any anomaly, predicting when the job is going to fail?
Let's think about that. And Nico, feel free to weigh in on this if you want. So if you're looking at application logs and you want to determine anomalies, well, this is a little bit related to that last use case in the template that I was mentioning before. And we've done examples of this where we've used this auto-encoding method. So, if you're combing through logs and you're looking for anomalies and you don't know a priori what those anomalies are going to be, then you're inherently in a sort of unsupervised case. In the examples that I've seen of this, we go through the following process. We take those logs. Typically, those are going to be in some non-standard format. I mean, if they adhere to, say, it's sort of Apache log format, then you can probably use standard connectors for turning those into tabular data sets, which is really kind of the first step you want to go to create sort of meaningful tabular arrays of data. Or you create some custom code in one of our streaming applications or in the data science platform that can connect to these log files and process them and turn them into something tabular. So once you've got that and you've got meaningful variables, let's say in the case of an application log, you're going to have a timestamp and you're going to have the type of operation, you're going to have the user who was logged in, and you're going to have the browser was being used, for example, if this is like a web log. Whatever those might be, those are going to be parsed out. You're typically then going to use some of the sort of pivoting and variable construction techniques, variable selection, feature generation techniques, maybe some sort of automated feature generation to build out meaningful variables using like windowing and time series technique to come up with things like, how frequently has this IP address contacted this application in the last hour is sort of the type of variables you want to do. And in our data science platform, just to push on that for a little bit, we have sort of standard techniques like this for doing feature generation automated in a manual way, and window functions and joins and filters and merges and so on, and normalization and null value replacement, all those techniques you want. I think what you're really asking is, like, how do you then find those anomalies? And again, I would draw attention to some of those auto-encoding techniques where we use neural networks with hidden layers to reconstruct data sets in lower dimensionality as a way of sort of smoothing out the structure of the data set, and then looking for things that don't conform to that sort of normal core set of data points and defining those as anomalous. And that's how we've done it at several cases in the past, mostly in manufacturing, but I think the same techniques can be used pretty broadly. So that's sort of my fairly general answer for that, I think.
Yeah, I would
Okay.
I would just add on to that real quick, Stephen. I would definitely emphasize, the first step is getting it into some sort of tabular format. Can you get some meaningful features or variables out of raw text logs? Because once you're able to do that and get it into a more traditional tabular format that is copacetic with traditional machine learning models, then I think you're ready to cook with gas. As Stephen mentioned, one approach is an autoencoder, which is what we've primarily been using in the past few use cases. But there are a lot of different techniques to find anomalies or rare events. I know, particularly within the finance industry or finance world, there's a lot of interesting work going on as to finding anomalies or finding rare events. So I would encourage whoever asked the question or whoever is interested to look more into what are some of the bleeding edge techniques that are used in the finance world to find fraud or other anomalies.
Steve and Nico, thank you. Great answers to some very good questions. For those of you that asked questions that weren't answered today, we will be sending all unanswered questions to Stephen and the TIBCO team so that they can follow up with you after today's webinar. I have just a few quick announcements. Please mark your calendars for May the 7th, 2019, and our next Data Science Central webinar, The Human Side of Organizational Change, Lessons from Tableau's Engineering Team. Also, today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. And past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful insights into a wide variety of topics of interest to our data science community. This brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to TIBCO for their sponsorship, as well as to our speakers today, Stephen Hillion and Nico Rod, for their insight into today's topic. My name is Rafael Knuth, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on May the 7th, 2019. Have a great day.